Okay, folks. I think I'll go ahead and begin. So you've had some time with your mentors, and you've had some time to see a lot of stuff out here. I know that when I had a new student come into the branch or a new employee, particularly a new student, a young student, they'd get into a training program here at the Langley, and for the first year or 18 months, they would be able to go around the center and visit the wind tunnels and the labs and the fab shops and all that. And I was always jealous because I never got to visit all those things. You're getting to see things that many of your mentors probably haven't seen, or if they did see it, they saw it 15, 20 years ago, and it's much more state-of-the-art now. Have you been to the fab shop where they do the free-form welding? Oh, that's wonderful. Hope you. Oh, they can see the free-form welding. I don't know.
Where's Karen? Karen.
Yeah, that's where they, you know, on 24/7 basis, they build up. This is a modeling and simulation activity because you do a computer-aided designed, you know, 3D rendering on a computer, and then it automatically builds up the model or the object using basically free-form welding. So they have or free-form lasers. So they have various materials, including alloys, and they can change the mix in the alloy because they can bring two metals together and just build up this thing automatically by robotic manufacturing on a 24/7 basis, and they can do as many as they want. You don't have to have somebody working, you know, shifts and skills to bring in. So I think it's a really neat thing. In fact, they can change the alloy component. Well, that's an area of modeling and simulation. The reason I bring it up here, it's exciting for one thing, and secondly, it's an area of modeling and simulation that has developed in the last 10 years or so, to the point where now the objects that they make are not just cute objects they've created, but they're certified to go into wind tunnels. So to go into wind tunnels, you have to make sure they're not going to break and they have certain value, you know, and they represent what you want to do. So these have now become useful objects. They've gone from interesting technologies to useful objects, and that's kind of means they're at the level now of innovation, because now they're useful to society, useful to people. All right, so let me, I'm going to talk today about modeling simulation with some examples, and it's going to be kind of Monday's talk, the introductory talk, but expanded, and we can answer questions and ask questions and so forth. I'm going to spend just about 20 minutes on this, the same thing I did before, modeling simulation, content standards, and engineering, the S&E of STEM, to make sure we're all straight on where E fits in STEM. Because oftentimes, as I've said, people, the political power say we need innovation, therefore we need STEM, and then suddenly it becomes, therefore you need to have your kids take another math or science course. And so we'll talk about, well, no, what you really need is the E of STEM if you want innovation. So we'll talk about that in a few minutes. Then I'll give you a number of examples. I didn't do this Monday because of the short time period, a number of examples in the real world of how modeling and simulation is used. And then we'll move around a little bit, do an audience exercise, which is that mammoth extinction game I talked about Monday, but we didn't do. And then I'll demonstrate how to do that with actual software, STELLA software, doing the mammoth extinction game theoretically with that probabilistic model. And then we'll have some time for questions and hopefully answers. As you guys and gals go back to your school divisions, I know as a teacher you don't always have a whole lot of input into what goes on at the policy-making level, but to the extent that you do have that input, please recognize this three-legged stool. What we found in Virginia in 2007 is that the standards, the state content standards and decisions about courses, and are still being made in the Virginia Department of Education, our State Department of Ed. And the skill set in our State Department of Ed is very limited. They're basically retired teachers who at one time actually knew pedagogy, knew how to teach, and knew some content stuff. But if they've been in the department for 20 years, they've gotten more into management and don't know that. So it's them, and then they get some K-12 teachers on panels, and they decide what the standards should be. What we found in 2007 was really there's a piece missing from that, and that is subject matter expertise. I found the day I left graduate school to start teaching in 1971, that my skill and knowledge of what was happening in particle physics started to decline very rapidly. When I was in the physics department, day in and day out, I knew exactly what was going on in the world. I knew what experiments were taking place at CERN. I knew what was going on at Brookhaven. I knew, because you've just had those conversations all the time. But as soon as I left, you missed those conversations, and after a year or so, you learn from Physics Today and Scientific American and things like that. So it's important to have subject matter experts developing standards. And you see subject matter experts out here, and you have subject matter experts, I'm sure, in your state, in your community, people who actually do science, practicing scientists, practicing engineers. And that's what we did in 2007. We brought them from universities, government labs, and industry, because university scientists can kind of study what they want, what they can get funded for by NSF. So it's basic and applied research. In government labs, we do applied research and development. And then in industry, they do development, manufacturing, and operations. So bringing these three perspectives together, from practicing subject matter experts in physics, chemistry, biology, engineering, is really important to getting good standards. So I'm going to lay that out for you. I know that in California, when they did the standards many years ago, they did have subject matter expertise. So I'm just laying this out, that it's something that's often missing, both for content standards, for textbook approval, things like that. So you can do it. It's just a matter of putting these folks together. By the way, when we did that, we found that the Virginia Science Standards, they were ranked by Fordham as number 2 in the nation in 2005, Virginia Science Standards. We found that, well, that's nice, but they were dated to the Sputnik era. They were 1960s standards. Because Fordham only counts about 1/3 of their points for content. They look at lots of other things. So you can get a really high score, but your subject matter could be dated, let's say. So one of the things, that's just a long lead-in to say, so we recommended to the State Board of Education that they make some changes, and one of the changes we had recommended was, in this day and age, modeling and simulation really needs to be in the science standards, and particularly as you do experimental observations and your experiments and your lab work. And so the board, State Board of Education, took this seriously, and so now we have, and these are examples, this is what they look like. Nothing fancy, it just says that in physics, models and simulations are used, okay, to visualize. In biology, appropriate technology, including computers, graphing, calculators, probeware, et cetera, and modeling and simulation, modeling concepts. So what you see is grade 6, middle school and high school in Virginia, all children will be exposed to modeling and simulation. And what it means is a teacher can't say, well, I can't teach that because it's not in the standards of learning. Because we have teachers who think the standards are the whole course, not a base of the course, and all they teach is the standards. So now it's in the standards, it'll be assessed, and so it's now, so Virginia has this. There's a way to put these into your standards. Now, let me spend a minute or two. So the story is we had subject matter experts come together from universities, government labs, which includes the Department of Defense, Energy, and NASA, and industry, said this is one of the things you need to do in Virginia. And by the way, they could point out that in Virginia, there was, under Governor Mark Warner several years ago, a modeling and simulation initiative. So the General Assembly was already supporting in the state, at the industry and university level, an initiative in modeling and simulation, yet K-12 didn't know anything about it. So we pushed hard to get this in. Okay, so the other thing we're missing, besides some of the content in science, is an understanding the difference between science and engineering. Much of what you see out here is engineering as you go around. There's some science, but it's more engineering. So science, by definition, is the understanding of the natural world and the nature of our world. And then engineering is about the human-made world, the designed world, solving problems of society. Innovation is about the creation of new value. So someone says they want innovation, that means they need new value. And the point of this is that comes out of engineering, not out of science. Science plays a role, but it really comes out of the engineering design process and engineering. And so, which is, you'll see in a couple of slides, not really embraced in K-12. So here's an example. The problem when I was a kid, in the late 50s and 60s was that Russia had put Sputnik into orbit, and Russia had a perceived lead in space program. Russia also had some very large boosters and had exploded both a fission bomb and a fusion bomb in the 50s. So it was called the Cold War, and the United States was very afraid of not only the Russians launching missiles to blow us up, ICBMs, but also now they had Sputnik up there. How hard would it be to put a nuclear weapon on a satellite and just drop it? You know, a Sputnik went over every 90 minutes. Sputnik's only like this big, but it went over every 90 minutes, and there was fear. And so the problem that was being solved here, and so President Kennedy said, well, we're going to show you who's best, which society can do the best, the societies being the democracy against the communist system. The one that does the best, we're going to go to the moon. We're going to take men safely to the moon, return them safely home before the end of the decade. That was a challenge. Well, we weren't going to the moon to learn what the moon was made of. We weren't going to the moon to learn any science. We didn't care about any of that. I mean, we said we did. We did experiments and stuff like that. But the real issue was solving a political problem that the United States was apparently behind the Soviet Union, and we're going to leapfrog them with this huge engineering feat. Now, it's often called a science feat, but an engineering feat. Because what happened was, if you look at this chart, the math of going to the moon was pretty much calculus, differential equations, stuff from the 17th century. The science was pretty much Newton's law and some chemistry, again, 17th century. In fact, I would say if you had to discover something in science in order to get there, you couldn't do it in 10 years. You don't know how long it takes to discover. I mean, science you're trying to discover. It could take, a day, it could take a year, it could take forever. We had some of the technology, which we improved on, rockets and protective clothing and so forth, and computers came about. But the innovation, the real thing of getting humans to the moon, returning them safely to Earth, and I will say that the hard part of that was returning them safely to Earth. Getting to the moon wasn't that much of a problem, but getting back safely was with humans. Took engineers and many other professions, and engineers had to bring this project together and understand this is what we need to do, here's the desired result, and how do I pull all these pieces of technology and math and science and skills and politics, because I have to have it funded. How can I pull all these together to get where I'm going? Okay. Any question on that? Now, some scientists can become engineers, but the sense of the engineering design process is to solve problems and bring pieces together and achieve a result that's acceptable. Someone has certain things they want, you have to give them a result that may be what they want, maybe what would be acceptable to them, because they may not be able to achieve exactly what they want. The recent Gulf oil spill last year, there was New York Times, inside the Times, one side of the page, had a headline, scientists, I underlined this, scientists are focused, little headway on leak made by engineers. And the other side of the page, it said, scientists build a case for undersea plumes. Scientists were trying to understand these undersea oil plumes. Trying to understand them. Engineers were trying to close and stop the leak. They were trying to do something for society. Now, what the scientists learned about these plumes would be used by engineers the next time. They could take those data and say, okay, now we know more about these plumes, we know more about what happens, and we can make better blowout preventers and things like that for these deep sea missions. So a clear, and this is a place where the New York Times gets it right. A friend of mine jokes, he's a professor of engineering at Duke, Henry Petotsky, and Henry jokes that whenever NASA has a success, the scientists get credit. NASA scientists do this. When they have a failure, NASA engineers, fail. So the engineers get blamed for failures, scientists get credit for successes. And maybe it's because scientists don't really have failures because they're just trying to understand. They don't have any due dates. So here's a place where modeling, simulation, and science and engineering cross over. On this chart, I used this Monday. This is, if you're going to Mars, let's say, to find out if there's life there, scientists tell you what it is you need to know there's life there. Like, do you have to measure carbon dioxide? Do you have to measure waste products? What is it you have to measure, and how well do you have to measure it? They will tell an engineer or an engineering technologist, an instrument maker, this is what we need to measure. The instrument maker or engineering technologist say, okay, I'll create an instrument, or I'll take one off the shelf because I know what's up there, or I'll have to invent an instrument to do that. And they'll do that. And what often happens is the engineer then comes back to the scientist, says, hey, I got this instrument, check it out. It seems to do what you want. The scientist says, yeah, it does. And so they go together to the project engineer, the spacecraft engineer, and say, okay, here's our instrument. And the spacecraft engineer looks at it and says, well, this thing that's half the size of a room, or says, that's nice, but your mass budget for this project is a kilogram. And this 600-pound thing you built, we can't put that on Mars, and we just can't do that. And so, okay, so they go back, and then the engineer says, well, I can't make the measurements with that, but I can make this measurement at this accuracy, this precision, and the scientists will say, well, that's not good enough, and they'll play back and forth until they get a result that gives the scientist the result he needs, and also gives the engineer what she needs to be able to land this thing on the moon, to get the payload there. So this is back and forth engineering design process. And now, for a lot of what they do, and you heard some of the talk about this by Juan Cruz on Monday, they also have to figure out now, how can I land this thing? How can I practice landing this thing? So they do simulations. They do simulations of the blast off, on the rocket from the Earth. They do simulations of the reentry, of the path, because the path as it goes from Earth to Mars is going to be disturbed by other planets. You have, the gravity of Saturn, gravity of Jupiter, all these things. You have flares from the sun, radiation pressure that's going to drive it off course. So all these things have to be accounted for. And they do that through a simulation to prepare for this flight. And finally, the entry, descent, and landing in the atmosphere, they need to know some things. Like they need to know, what's the atmosphere made of? How thick is the atmosphere? What's gravity like, from my entry on down? And these things they know a little bit of because scientists in earlier flights have taken those data. Scientists have learned about the atmosphere of Mars. Scientists have learned about the surface of Mars. They know that when you're coming down through the atmosphere, there are places where there are mountains. There's places they call sea level and places that are valleys. And so you kind of don't want to be cruising down to land on something you call sea level and suddenly find yourself at a 5,000-foot mountain and go crashing into a mountain because you're going too fast to land. So you use the information from earlier scientists and you develop these simulations. And then you say, I don't know that stuff perfectly, so I put error bars on it. That's what Juan said, these Monte Carlo simulations, where you do simulations of various outliers taken in various combinations to see that your mission can be successful. This is what engineers do in order to get the data or to get the instrument in place so the scientists can get data. Okay, any questions on that? Is that stuff you guys already knew, or is that kind of new to you?
No, we know.
Pardon?
We knew it.
You knew that? Great. You guys are a great class.
I have a question.
Yes, ma'am.
I've heard the term Monte Carlo. I have a basic idea of it, but if I were to give a definition of that to a student, what would that be?
So a Monte Carlo simulation, so the question is, what's a Monte Carlo simulation? It's just a simulation, if I can use simulation in the definition, because I'm defining Monte Carlo part of it. It's a simulation which takes into account not only the conditions you would like to have, you think you're going to most likely have on carrying out a mission, but also a range of off-nominal conditions that you might get that you're not expecting. So in other words, you think you can come down through an atmosphere that has a certain density profile, but it might be you'll hit some density you weren't expecting, or some winds you weren't expecting, or some dust storm. So what you need to do is you say, okay, I think I know the atmosphere, and I only know the atmosphere to some level of accuracy or certainty anyway. Because Earth's atmosphere varies day to day, from morning to night, depending on whether the sun's on it or not. So you look at a range of atmospheres that you might go through, and you don't just look at that, but you look at those in combination with ranges of if the vehicle is at the exact angle I want it to be coming in at, or 5 degrees this way or 5 degrees that way, or if it's vibrating, oscillating back and forth. So a Monte Carlo simulation is just, it sounds like a crapshoot. That's what it is, because you're landing, because your engineering problem is a crapshoot, because there's lots of stuff that's changing. It's the real world, and so you don't know exact answers. Does that help?
Yes.
And you can usually use a distribution about this nominal condition you want, but sometimes you have to be careful, because some people will go, okay, so I'll go 10% this way and 10% that way of these values. Well, a percent, think about it. Suppose one of these values is minus 0.1, minus 0.1. I can take as many percent of that as I want, 10%, 20%, 50%. I'm still going to be negative. But if I change the sign of that thing from negative 1 to negative 0.1 to plus 0.1, I may change the entire stability of the system. The system is defined by a certain stability. So you have to be careful when you do Monte Carlo simulations to make sure you exercise not just percentage changes from nominal, but also potential sign changes, which would change the nature or the stability of whatever this dynamical system is that you're doing. So I've seen that if you're just in the theoretical world of Monte Carlo simulations, doing those because it's an academic exercise, when you get into the real world, you can really, you have airplanes crash on you. Because you didn't do this change. All right, so where is this in K-12? So if you guys already know this difference, you also then know that in K-12, we have a world that has math and science that are kind of in what we call the instructional program often in states. And then we have trades over here in the CTE or career and technical education world. Oftentimes engineering is lumped into CTE. Oftentimes it just happens at some schools where they want to have it. Like in Virginia, there is no engineering endorsement for a K-12 teacher. If you want to teach engineering in K-12, you have to get a CTE or technology education endorsement, which I liken to having a science teacher getting a math endorsement. And so just letting you know that we use this chart often to talk to policymakers about what we call the gap, that if you want innovation, you kind of need engineering. Engineering has a combination of theory and hands-on components, whereas math and science are mostly almost all theory, and trades are almost all hands-on. The example I like to give is that in auto repair class. So in CTE, because this is for kids who get high school degrees with some national certification like NOCTI or something like that. So they take a course. It could be traditional trades such as welding or plumbing, or it could be 21st century trades like computer repair, network administrator. But still, they're preparing to go out into the world with some capability. They're prepared to build and repair existing systems. Engineers are prepared to design and build new systems. That is, they're prepared to innovate. So here's the example. I've got an auto repair shop in a school, traditional CTE class. Student learns that car comes in, they do the analysis of what's wrong, they go to the shelf, they get the new part, and they replace the part. They repair the existing machine. An engineering technologist who oftentimes has 2 years of college or on-the-job training for a few years in the real world can not only do that, they can analyze what's wrong with the car, and suppose the part's not on the shelf, they have knowledge of things like CAD, CAM, so they could go out and actually manufacture a new part, replace a replacement part. The engineer has knowledge not only of these parts and fabrication processes and so forth, but also knowledge of chemistry and metallurgy and so forth. So the engineer might say, oh, this part needs to be replaced, but I can innovate a new part, maybe one out of a polymer or an alloy, and I can put something together, a composite that's better than the other part, something that may be lighter, it may be cheaper, it may be environmentally more friendly. So that's what the innovation's about in engineering, and that's how it differs from our traditional trades courses. And it's very, very difficult, at least it has been in Virginia, to get any movement on the system that's in place, which says you're either going to college or you're going out directly to the workplace. And the engineering role is you're going to college, but your focus is going to be on what you do in the workplace. Okay. Questions or comments on that? Yeah.
In your ideal situation, what would happen then to close that gap in the K-12?
So to close this gap in K-12, I don't know what the actual answer is. I don't think it's to get the theoretical people in charge of engineering, because then it'll just become about engineering, not doing engineering. Is a danger of that. If you continue to put over here, these folks in general have tech ed degrees out of schools of education and don't really have the theoretical basis to do engineering. So I think the answer is to bring some engineers in to the K-12 system and go ahead and have someone with an engineering background in charge of this, and to put together the requirements for an engineering endorsement. So you can start getting high school teachers, certainly, who have engineering endorsements and get the engineering skill into the mix. So I think that's the most important thing, is get the engineering skill in, have the endorsement for engineers, so that they don't have to go get a tech ed endorsement in order to teach engineering. And on the other side, you don't have tech ed people trying to teach engineering when they're lacking some of these skills they really ought to have.
How do you attract those type of people to a school system that pays them considerably less than they could make?
Yeah, so, but all teachers get considerably less than they can make in the outside world. So, and I think one case is, one of the concerns in engineering right now is we're losing, engineers are retiring, and my generation is retiring. And a lot of us are still have a little life in us and may like to go teach, career changers from the military, from government. So you have a lot of people who are looking for jobs, but they can't get them. They go to the school system and say, hey, I'm an engineer, I built the space shuttle. And they say, well, I'm sorry, you're not qualified to teach, until you pass your praxis in tech ed.
Yeah. Would you take the job if you got $30,000 a year?
Yeah, if I'm retiring, well, and I don't know. I mean, we have all, I was a big believer in the Peace Corps. I was a big believer in the Peace Corps. And I think there are people who come out of college who, for a couple of years anyway, will want to teach. And they, teach for America. I mean, people are going to do this for a couple of years. The point is that if they're engineers, there's no place for them in our system in Virginia. They say, I want to teach, but now they have to go back and get a tech ed qualification and take praxis in tech ed and move on. So I think there are people out there is the answer. I think they're out there, but they get pushed away by the hurdles they have to jump. I mean, they should take professional education courses just like a math major. I mean, we have math majors teaching math, physics majors teaching physics, biology majors teaching biology. Why wouldn't we have an engineering major teaching engineering? And the engineers don't make that much more than scientists and mathematicians in the outside world.
They all make a ton more than teachers.
Yeah.
I have a comment and a question. In Texas, we have something called ECAP. It's Education Career Alternative Program. It's for probationary certification for engineers, perhaps, or anybody with a degree to come in and then they can teach. And then my question is, would our first step be to contact our superintendent and principal to try to get this in our school?
Yeah, in Virginia, I mean, states work pretty much the same. Virginia, we have the same thing. We have alternative certification. When I started teaching in 1971, I had, all physics and math that I needed to teach, but I didn't have professional ed courses. So for 3 years, I took professional ed courses while I was teaching to get my professional certificate.
It's a summer program now.
Pardon?
In the summer.
Okay, so yeah, and I know as things like UTeach in Texas have become more popular to actually get in subject area degrees, they've been doing this. But I think the answer is, yeah, the superintendents, and I would think the State Superintendents Association could have influence on the state departments of education. I've been going to our state board trying to get their ear for this, and is semi-successful. But I think Superintendents Association for the state, Association of State Superintendents, is usually pretty good. Now, there is mention of engineering in the new science, NRC framework of science standards that came out. I'm not sure how that's going to play out, whether engineering is going to kind of be rolled in, or if it's going to actually be a separate element, or how that's going to actually turn out in the standards that come out. But my recommendation to you have engineers. There are plenty of courses, engineering courses around. Curricula, there's Project Lead the Way, which is a national program. It's a turnkey program. Each state that has it has a university engineering school in charge of it, and they provide the training and the certification that schools are actually doing the right course. When I talk to Project Lead the Way teachers who did not have an engineering background, they really struggle. Even the best tech ed graduates I talk to struggle a bit in teaching that course. There's children's engineering. There's engineering as elementary from Massachusetts. There's a Virginia children's engineering in K-5. They're aligned with standards of learning in other, it's not like you take engineering, like Virginia Children's Engineering is basically about design, engineering design and manufacture. So suppose you just finish reading The Three Little Pigs, there'll be a design brief, one-page design brief that says, build a wolf-proof house. Okay, so here's the equipment you can use, the components you can use, and you get kids together in teams and they brainstorm. Have you guys seen something like this? Okay, so you have a design requirement, a wolf-proof house. So so it reinforces The Three Little Pigs, what you've read and things like that. But kids start working together and they brainstorm, what they're going to do and how they're going to use this equipment. And there are lots of different answers. So you have 5 different teams in your room. You get 5 different answers of what this looks like, how they use this equipment. Well, that's okay. I mean, there's no one right answer in an engineering problem. And so then the proof in the pudding at the end of the day is the teacher comes around with a hairdryer, which is the wolf's breath, and says, are these things really, wolf-proof? And there are ones where you're studying the colonies. You're studying the colonies in the founding of the nation. And so you learn they have different types of houses in the New England and Mid-Atlantic and the South. And so you have to build a fort or build a house for these areas. So kids actually have to get involved in the design and understand why they're designing the house this way for the part of the country they're designing it for. So these are all ways that integrate and reinforce the current standards in all the other courses, but teach kids the engineering design and problem solving process and get them working together. They're using all the 21st century workplace skills as they do this. And there are lots of extracurricular activities from the FIRST programs of Junior Lego League and Lego League. FIRST Tech, do we all know about FIRST Tech? Not FIRST Robotics, but FIRST Tech. Okay, FIRST Tech is a kind of a junior FIRST Robotics is a very expensive, big program, and it really requires an engineer as a mentor to building these big bots. I mean, they're this big. FIRST Tech is a program that has smaller bots. As a matter of fact, they have to fit into a cube that's 18 inches by 18 inches by 18. They can expand out from that and do their stuff. But they have all the requirements as far as moving and building and stuff like that as the big bots. But they're a lot cheaper. They're a tenth the price to run that program. So it's about $2,000 a year to run a FIRST Tech program. It's about $20,000 to do FIRST Robotics. Is
that under the same umbrella as FIRST Robotics?
Yes, FIRST, yes. And it used to be one called VEX, and VEX moved off on its own, and now FIRST has put this thing called FIRST Tech. But yeah, to me, it's the best value they have, and for middle school and high school kids, it's terrific. And then of course, FIRST Lego League, the elementary, and then ages 9 to 14. There are lots of others. This PTC Real World Design Challenge is the PTC is a corporation that makes major design software, CAD software, like Pro Engineer. And they make Pro Engineer available to you for free to do the design for this Real World Design Challenge. And they give you training to use it. So you can get lots of stuff that's out there in these extracurricular activities. If your science fairs in your school are still called science fairs, I strongly suggest you change them to science and engineering fairs. It's likely you already have an engineering component. One of the groups is something engineering, mechanical and civil or something like that. The Intel International Fair is science and engineering. It's called that. And they have separate evaluation sheets for science projects and engineering projects. So in Newport News until just last year, they were judging the engineering projects by the science rubric. So kids were trying to fit the engineering they did into a hypothesis and conclusion, and it doesn't work. So now, if you go to the Intel site, you'll find the engineering rubric for evaluating engineering projects. It's different than the science project. Okay, so that's you're at NASA and we have engineers. We have rocket engineers, not rocket scientists so much, and that's the advertisement for that. Any questions on E and S? Okay, so what's different today? And you saw this slide on Monday. What's different today? I have a hard time standing still when I talk. I like to walk around. Speed and memory of computers, of course, and allows kids, we said the other day, and Juan said also, to stop thinking about a static world and a single answer and thinking about a dynamic world, how the world changes over time, behavior of things over time. And we went through this thing the other day. Here's the Roadrunner. I talked about the Roadrunner and what do you need to know when we talked about the, you have a rock on a cliff that Wile E. Coyote's going to push out and squash Roadrunner, and you say, you know that when he pushes the thing to the edge of the cliff and over the edge, you know what's going to happen. Why do you know? Because you have a model in your head, and the model is of what? Gravity, yeah, gravity. So gravity, is if there's no longer a cliff there, the rock's going to fall. So you have a model in your mind. So you run a simulation in your mind of what's going to happen. So modeling and simulation has two parts. It has a model and a simulation. The model is some approximation to the real world. It could be a mathematical approximation, a physical approximation, a combination of the two. And then the simulation is actually integrating that model with the world and running it forward in time to see what the behavior is over time. So in the Roadrunner case, the model is there's gravity and this rock's going to fall and squish the Roadrunner. And so you actually see that in your mind's eye. That's the simulation. You also could have the cartoon itself, which would do that. And I'll talk a little bit more about that in a minute. So I say this could be a simple cartoon like a static picture like I just showed you, and the Roadrunner is going to get squashed. It could be an animation. You saw Juan Cruz do a number of animations of landings onto Mars, or you could have a cartoon on the Saturday morning show where the rock falls without any specific rate at which it falls. It just falls and hits the Roadrunner. Or you could have actual physics equations. In other words, this rock would fall in the Roadrunner cartoon according to Newton's law, according to acceleration by gravity, 1/2 AT squared plus B naught T plus S naught, and you would see that, or F equals MA, you would see this rock fall and accelerate accordingly for 50 feet, from the cliff. The modern simulation could also be experimental, so it could be like a wind tunnel model, or take a river or bay model and scale it. Now, the scaled models behave differently than, say, the real airplane. Think of an airplane in a wind tunnel. Even if you did everything correct, geometrically you made all the lines and all the little dimples and rivets and stuff like that, and you scaled them all down and put for this model, still that model would not behave exactly like an airplane in the real world when put into the wind tunnel. Can anybody tell me why?
Scale.
What didn't you scale? You scaled everything on the airplane, but what did you not scale? Pardon?
Reynolds numbers.
Air conditioned Reynolds number, yeah. Numbers
Reynolds number.
is always the answer, right? Oh, it must be the Reynolds number. Yeah. So that says the molecules of air in the tunnel are still the same size they are in the atmosphere. So you didn't scale those. Say, well, how could that matter? Well, that's the fundamental issue of turbulent and laminar flow, is the cohesiveness of these air, the medium it's going through. So these are all approximations, and a lot of engineering is knowing how to bridge from the approximation you're making to what's going to happen in the real world. So you can have these physical approximations, and then you have hybrids. And when I say hybrid, I mean that you could have a physical model and a human. So you have a human pilot flying an airplane. So if a pilot gets into a simulator, well, you've got the real pilot there. So that's the real thing, the real human being, how the pilots can behave. The simulator is an approximation to the airplane. So they're mixed together in some way. So you can have those too. A quick favorite story on Formula One. So Formula One this year, anybody follow Formula One racing, open wheel racing? It's like IndyCar on steroids. And so the international version. So in Formula One this year, there's a rule the last 2 years, you can't do any practicing. It's to help the smaller teams compete with people like Ferrari and Mercedes who have a lot of money and can practice and do things all they want. They said no practicing. You have to do everything basically by computer simulation until the actual practice days for an event, a race event. So they come in I think on Thursday or Friday to a race event that's on Sunday, and they get to practice. And what they do is they have simulators, and so they go back to their companies, and they have a simulator of a model of the car, a math model of the car, and they have a cockpit like you're in your car, the race car, and they have a model for each track, a math model for each racetrack, and the drivers practice these tracks. the way a car stays on the track going around turns is both from the friction due to its tires in Formula One, but also suction underneath the car, because it takes air under the car and expels it out the back in such a way that it makes a vacuum and it sucks the car down to the track. A Formula One car going 180 miles an hour would be, you could stick on the roof. I mean, they pull 4 Gs around turns. So, you know, how can you couldn't get more than 1 G, right, from tires, because it's the normal force times the coefficient of friction. But that's how much force these things have going, you know, from these aerodynamics. So they have these aerodynamics, you know, holding these cars down. So the cars have to be very close to the ground, and this stuff has to be modeled very carefully. So all these guys prepared for going to the British Grand Prix last year on a track that had just been revamped. They just put a new section to the track, and they had the new section into their simulators. And everybody practiced and practiced. They came to the track. Long story short, every one of these drivers, and these are the best drivers in the world, every one of these drivers got to this one turn and shunted off the track. Just went flying off to the side. It turned out that when they matched this new section of track to the old, there was a small bump. And nobody had modeled that bump in the track model. So what that did when you got to that small bump is you lost the suction momentarily as you went into this turn. So the drivers had practiced, you know, having a nice flat track and having that suction, that traction going in. But now they got to the real world and suddenly they didn't have it anymore. So this is why, you know, models are important. Models are important. And we talk about Monte Carlo simulations. Maybe part of a Monte Carlo simulation is to put some bumps in around the track on turns like that and see if you're dealing with we call it robust, in a robust way, things like that. And this is just a matter of, okay, so what about gravity? That's something simple. So you have D equals 1/2 AT squared. I'm sorry, the rock could simply fall. It could fall according to being in a vacuum. D equals 1/2 AT squared. There's no air resistance. Or you could add air resistance into a model, make it a little more complex. You could realize there's air resistance with variable density. For example, something coming from much higher, the air density changes, and you might want to put that variable density in. You have what's called the standard atmosphere book published, and it'll tell you what the density is on a given day, and in general, given altitudes. And getting back to the question on Monte Carlo, you want to vary that density through the atmosphere and have little areas where it changes to make sure that you've taken into account the range of densities it might be. You might have variable gravity from altitude, or if you're going into the moon, we found out years ago when Ranger and Lunar Orbiter came over the moon that you had things called mass concentrations. The moon was not homogeneous, but the areas of the moon had concentrations of mass that weren't in others, so that the orbit, you know, varied according to that. So you can, and then you can put other things in. So the model can vary according to the complexity you need for the problem at hand. So it's an engineering for the problem at hand. Okay, so here's a picture. We talked about a physical model, wind tunnel model. We talked about that. Modeling can be used for engineering design. It can also be used for training. So for the space shuttle design, millions of simulations were probably done, even in the 70s, 60s and 70s, to get the number of designs for the space shuttle down to a few that could then be tested in wind tunnels. It's expensive to build models and put them in tunnels and run tunnel tests. So you don't want to test everything in the world. So you run a lot of simulations to down select to a few models. That's part of engineering design. As far as missions, training, so you have engineering training. Every mission, as you know, the astronauts spend a year training for these missions. They do everything they're going to do on the mission hundreds and hundreds of times. They can do it in their sleep. They know the mission by heart. They go into the neutral buoyancy. The neutral buoyancy pools at Houston at the Johnson Space Center, and they go underwater and practice like in a weightless environment, doing all the maneuvers they have to do in the spacecraft, outside the spacecraft, you know, hundreds and hundreds of times. The neutral buoyancy pool is a simulator. It simulates what it's like in space. Is it exact? No, but it has a lot of a lot of the elements of space. So training the pilot that flies a shuttle back does approach and landing thousands of times in a shuttle simulator. It's a jet airplane. It's been redesigned in such a way that it behaves like the shuttle. Okay, it behaves like the shuttle and practices time after time again, the approaches. So it's a training mechanism as well as a design mechanism. Here's the design in the DoD. For years, aircraft carriers, everybody's watched Top Gun, I assume, at some point in their life, and you see the airplanes come in, what's kind of a controlled crash into the deck, and they grab this wire and come to a quick stop in 2 seconds, from 150 to 0 in 2 seconds, something like that. And so, is there a carrier pilot in here so I don't make a mistake? I'll get corrected here. All right, so the approximation is a model. So my model of what happens is an approximation. It's pretty close. So there are 4 wires. Traditionally, there's always been 4 wires. You come in, and you hope you hit the 2 and 3 wire, because you hit, the first wire, that meant, boy, you were pretty low, and if any lower, you would have, gone into the fantail. If you hit the 4th wire, that meant that was your last chance, and if you were any higher, you would have had to go around and make some decisions, and So you like to hit the middle 2. Well, it's expensive to have 4. Each of those wires, you have to build them, you have to maintain them. They take real estate up on this boat. You have people that have to do that. So if you could get by with 3 wires, that would be better than 4. It's a small change, but it's better than 4. It'd be cheaper and simpler and give you some more real estate. So when you're bidding to build an aircraft carrier, you look for things like that, give you a competitive advantage. So the Northrop Grumman, Newport News Shipyard people said, hey, we can do this with 3 wires. And, but you can't just go to the DOD and say, hey, we can do it with 3, trust us. And the DOD procurement guy says, oh, yeah, sure, here's $5 billion. We trust that it'll work fine. What you do is you do simulations. And that's what they did. So they put together a simulation of a carrier deck, and they got carrier qualified pilots to come in and fly simulated, F-18s and F-14s and CODs and everything, to fly in to these decks with 3 wires instead of 4 and see whether they could land and see what they thought of it. What did the pilots think of that? They also did it not just flying into the deck, but they also did it on the rolling deck in a storm. They did it nighttime, rolling. So all the conditions you might expect to find in an operational world, they went ahead and simulated. Now, is that perfect? No. But it does give you a good feel for whether it's a stupid idea, an idea that has some merit, or a really good idea. So that's how it's used in modeling simulation. But you have to realize they are simulations, they are models. So as you look at that, you kind of put some error bars in what you hit. Many other fields, antibiotics, how they work. They do simulations, robotic surgery, how pandemics and epidemics spread. You can predict how things are going to spread from exposure to various viruses or bacteria and so forth. Predicting the weather, predicting hurricanes and tidal rise. So in Virginia, we have an issue with hurricanes and nor'easters, and they push the ocean water into the bay, into the Chesapeake Bay, and then up the river systems, and the water level can rise anywhere from just a couple of feet on a mild nor'easter to 9 or 10 feet in a significant hurricane like we've had in the last few years. And so people model that. They model the hurricane, the winds in the hurricane. They model the fact that that's pushing water as it sits out in the Atlantic toward the shore. They model the fact that it's either a full moon or not a full moon, so you have 6 inches or 12 inches difference in the tides. And so all these things have to be modeled. That water keeps getting pushed in through the capes. That's this area right here from the ocean into the bay, and then it can't get back out because the wind is still pushing on it. So it keeps getting pushed in, but it can't get out as long as you have this east wind pushing on it, and depending on how long. And then you have in the mountains, you have a lot of rain, and the rain comes down the river systems, and the rivers then meet the tidal water, and you get it. So all these things are modeled, so they can predict when a storm's coming what it'll mean to the people in the area, so you know whether to leave your house or get your boat out and things like that. I just have a couple more here. So this was an interesting one, and I'm going to tie down here. About 15 years ago, one of my engineers who was a pilot said, he can go home and he can see radar as to where all the storms are, but when he's up in his airplane, he has to read this silly text called METAR, and it's got a bunch of letters and numbers and stuff, and you have to decode that as to what it means about the pressure, the winds, and he says, you know, that's silly. So, you know, if I got a storm coming, I'm pretty busy, and and the technology's there. I can look. I should be able to look and see where the storm is and where it's going because I've got these, you know, these Doppler maps I can see at home on TV. So he started looking around. It's an engineering problem. So he went around the nation and he started talking to people, and he found that at NCAR in Colorado he could get lightning data from the entire country. They had, you know, real-time lightning data. Someone else had real-time Doppler radar. Someone else had, he had all these little pieces and parts, and he then put them together onto a single map, and so that you could see, you could put your flight path as to where you wanted to go, and then you could have this moving map display of where the storms were going, and where the lightning was, where the winds were, which airports were open, which ones were closed, all just to look at it. Say, oh, there it is. So I can say if I'm going here, I might want to go, the storm's going this way, so I'm going to steer this way around it, rather than, you know, fly into it or steer this way and actually, you know, have it envelop me. So he invented that, and that was an interesting technology. So the question was now, is it useful? Is it useful to the airlines, to the airplanes? So one of the first questions was, it's an engineering problem because I've got this new capability, but is it of any use to anybody? Yeah, he thought it was used to him as a pilot. So the airlines said, you know, our pilots know how to, with their eyes shut or in the dark, manipulate everything in the cockpit. They know where every instrument is, know where every button is. If I put another instrument in, like this display of storms, where does it go? Does it go to the primary flight display, the nav display? I mean, these guys are trained to know where everything is. So what they did was they did some simulator work. They put this thing in a simulator and a motion-based simulator. It's moved because you're in a storm, you know, you're coming up on a storm, you're moving. So they put it in motion-based. And they decided from that some places where it might go in the airplane. So they did a ground-based simulation for the airplane. And then two of the companies, Northwest and United, actually put them in airplanes in the fleet, and they used them back and forth to see if they did say, you know, what does it cost to put it in and maintain it versus the savings you get in knowing where these things are. So they actually did a real-world simulation with this thing. And so now it seems silly because we all know everybody has these, you know, moving maps and these, you know, you're used to that. But it took someone to invent this thing first and get it into the airplanes. By the way, one of the interesting things was the technology people, the computer people said, "Oh, you really want a touch screen, you know, because you want to be able to touch. We can give you a touch screen, make this real fancy." When they started doing the experiments in the motion base, bouncing around, touch screen's not so good because I'm being bounced around the cockpit and I want to know what the weather is here. And just as I go to punch there, the thing moves and I punch it. So they found really what's better is to have something where you could grab the side and have little bezel buttons so you can push the button. So his older technology was better in this case because of the real world situation. So that's a part of the engineering, is it's solving a problem, not just doing the best gold-plated thing you can get. And finally, this I think is my last chart on this simulation examples. Lots of times today on your laptop you have flight simulators and you can practice your flight simulation. So pilots will do that. Then they'll take their laptop into the training center. So you practice at home, they'll go to the training center and make sure that everything works the same way because you're in a different environment. Then they'll go to, say, a flat panel trainer. It's a partial cockpit. It's kind of like a cockpit, but not a full cockpit. And then finally, they'll go to the full flight simulator, which is just like, have you all guys been to our simulators over here yet? Are they going to the simulators?
Yes, on Monday.
Okay. So when you get in there, you'll see it's just like being in an airplane. I mean, I hired a guy about 15 years ago, and we took him in the simulator just for him to, because he's doing a little tour, and we had to get going. So I'm not the world's best simulator pilot, and so but I said, oh, we got to go. Let's land this thing. Well, you could have just gotten up and walked out, but you know, his mind believed he was so much in an airplane because the visuals were so great and everything was so great that when I banked to come back and land the airplane on the runway, when I banked, he grabbed the side of his chair. You know, he was in the pilot seat. He grabbed the arms of the chair because he really thought we were, you know, in his mind, even though he knew we were in a simulation, he thought we were tipping over. And of course, when I did a shuttle approach and got really, you know, and the ground rush was such that he knew we were going to crash, he pulled back like this. I mean, that's how realistic these things are. But they're models. So no matter what you do with that model, you get into the real world eventually. And the real world will always throw you things you didn't have in the model. For example, airplane models for the simulation are designed to fly where airplanes fly. They're training. They're not training you for unusual attitudes, like when the airplane gets upside down or does strange things. They'll give you an answer, but there's no value to that answer. So the real world always presents pilots in pathological conditions, things they can't really train for. That's why a lot of our pilots, airline pilots, are also glider pilots and aerobatic pilots, so they do get experience with all these different conditions that they don't get in their simulators. Okay, any questions on that before we start the Mammoth game? Comments? Was there anything new in there to you? Was that stuff you knew? Or?
Good.
I hope it's new stuff. So we're going to play the Mammoth game now, and I'm running a little 10 minutes behind schedule, but I think we'll be okay. So I talked about this Monday. The Mammoth game is a modeling simulation game. It's from a book. And by the way, I brought some examples of books here. I can leave them, and I'll pick them up Monday.
Oh, it's that Monday. Nice.
So it comes from this book, The Shape of Change, by Tukotsky and Quaden. And they're elementary school teachers from the Boston area. And they've put these together over the years, and I've modified a few of them, and a few of those modifications are now in the editions that we see of this. And so this introduces elementary school kids to modeling and simulation. I use it with everybody because I think it introduces everybody to modeling and simulation, which is why I'm going to use it here. What they have is a probabilistic model of a mammoth herd, and that's what you're going to do. And we've got, let's see, let's do three teams. I'm going to give each of you a package of 20 dice. You better count them. The last group I worked with were some tech ed teachers up in Richmond, and they kind of like dice, so I think I got them all back. So each die represents a mammoth. And so the 20 dice represent a mammoth herd. And by the way, this just shows you this aligns with some standards of learning and also many other.
This is the one where one.
It reinforces math standards and also some others. So
yeah, I sort of remember it.
So here's what let me just get your attention for a minute to say what we're going to do here. Because not everybody gets this. You have 20 dice representing 20 mammoths. We're going to see what happens to these mammoths over several years of their existence. And the way we know what happens is you roll the dice, and for every one of the 20, every die that comes up with a 1 on it, that mammoth has a baby. So you add a new mammoth in, and if you need extra dice, I've got some to add them in. A 2 comes up, that means that mammoth was killed by a predator. A 3 means that mammoth starved. So in 4, 5, and 6, those mammoths just go on another year. So you'll roll the dice, and you'll group them into 1s, 2s, 3s, and 4, 5s, and 6s. And for every 2 and 3, you'll pull them out of the herd. You pull the 2s and 3s out. For the 1s, you add 1 back in for each of the 1s. And then whatever you have left now is the second year, and you roll that, what's left. So you should not have, you might have 20 for the second year, but you should probably have 21 or 22 or 17 or 18 or 16, a different number. And that's the second year. And then you do the same thing there, taking the ones that have died out, putting new ones in, and you keep doing that, and someone keeps a record. So one person kind of rolls the dice, and one person keeps a record of each run, not of what each dice came up, but just the total number of mammoths. So on roll 0, you've got 20, you start at 20. Roll 1, you keep a record of, I might have 17. After roll 2, I might have 16. After roll 3, I might have 19. But you keep that record, okay? And then at the end of the 15 or 20 of these rolls, you should be down to 0, and then we'll we'll graph these up here on this board. Any questions? I mean, the model is a probabilistic model of mammoths' births and deaths. And it's a 1/3 probability they're going to die and a 1/6 they're going to live. Okay. So go, and so you can move around now. If you have to go to the bathroom or something like that, feel free. And I'll give you about 10, maybe 12 minutes to.
No,
5 or we roll them all
we
together?
roll them all. Well, the person takes a handful of them, and we just roll them, and then we got to pick out zeros, ones, twos,
Right.
threes.
So that's what
Twos
I'm
and
saying,
threes
do we
come out, and then the rest. So yeah. So Aaron got a
We each
handful.
roll
of
5
them.
or we roll them on that.
Why don't we?
2 herds are gone, and the other one has had 10 years. Well, it's had 10 years, and it's still living. So let's just go ahead and start graphing these. So 10 years is enough. I mean, that's part of the point of having a probabilistic distribution.
Oh, I got it.
We start with this group, and
I'm sure below.
guys, you'll watch this for a minute, and then I'll get you. Okay, so everybody started with 20. So your first year, what do you have?
17.
17.
Another 17.
Another 17? I'm sorry. No, I want these guys first. All right, and I'll get you here.
Second year was 7.
7?
7.
Lost.
Lost 10.
Whoa.
1 year.
It was a bad year.
It was a really bad year.
That must have been the. I was asked to avoid mass extinction. All right.
Then we were 7 again.
All right.
6. Year 5, we were at 5. Year 6, we went back up to 6. 7 was 6. 8, we dropped to 2. 9 is 3. 10 and 11 are both 1.
Oops.
12 is 2.
Which is interesting, right, going from 1 to 2.
Yeah, I'm not quite sure how we did that.
There's a biology lesson in there somewhere.
13 and 14 are 1s. And 15 we were extinct.
All right, so here's, I mean, this isn't very smooth, and I don't want to connect these because I don't know if this is a math lesson for kids. If I connect these dots, that says I know something about the time in between those years, right? I mean, so I don't have that data, but I can say, okay, this is what it is, probabilistic distribution, this happened. So let's do this table, and I think I'll use X's for you guys.
You have different colors.
Yeah, do a different color, clearly.
Well, I'm used to working with a colorblind boss, so.
Yeah.
I'm sorry, go ahead.
20, 13, 14.
Wait a minute. 20, 13.
14. 8. Bad year. Yeah. 4, 4. 3, 3. 2, 3. Another bad year, 1. And then we were dead. Oh.
All right, so two totally independent groups got kind of the same behavior. And that's the sense of the simulation. Now, you don't get exactly the same thing because it's probabilistic, but yes, sir.
In the simulation, do you have to start with 20 each time? What if your herd didn't start off as 20? That's part of this game, I assume, but.
Well, we did, so this game we do 20 is something, that's manageable.
I'm looking at something like if we were to make this a simulation for our classroom, or just my classroom. The little straw rockets, I'm sure you've seen those, give them a day to design it, and if they get a certain distance, they get a certain number of dice, if that makes sense. So they make it to Mars, they have no problems along the way, they get 20 dice, because their ship went 20 feet. If their ship from the design only went 10 feet, then they only start with 10 dice. And so their trip on Mars would not last as long because they had problems along the way. And so the better your design, your reward. And then you'd have the curve each way, but it would not be modeled exactly. You'd have that big gap, and there'd be a chance to reward the better engineering.
So you're going to change this from mammoths to astronauts?
Yes.
And that would be a great group project for the kids.
Right.
That do it one way, and then say create your own with a mascot or.
What do the dice represent?
The dice would be the same, like iterations on Mars. So each everybody's going to try to get to Mars. You build a little ship to get there. The better you ship, the more dice you have. That means you get to roll the dice, and each time you roll it, it would be like a year. You could say it's a month, because the little rovers are only supposed to last, what, 3 months? And they're up there for the last 11 years. So they did something right to get there. So they have better engineering, and they've lasted for 9, 10, 11 years. And so those kids who have a better design on their launcher will be rewarded with more dice. Obviously, theirs is going to last longer. The poor engineering would have, they may get lucky and have a long life on Mars, but probably not, because their engineering will not be as much. You reward them, whoever has the longest life.
So how does the dice, the one that we roll, fit into their?
Let's say that your team designs an excellent Mars system, and you get to Mars, you get the distance, and so you have 20 dice. And so you start off with a very high thing. It's assumed then your graph will tail out longer, and you'll be able to stay on Mars longer. My team only got half the distance, so I only get half the dice.
So when you roll the dice, so how do you roll the dice? What does that mean?
A month.
But you're not killing a rover.
You're not killing a rover, but the rovers die eventually. Just like the extinction of the mammoth, they eventually die. The rovers that are up there now.
Part failures or storms.
Yeah, so you have storms, you have part failure, you hit it.
That's what the dice represent.
Right, so one would be you hit a cliff, 2 would be, you know, there's a massive storm, 3, 4, and 5 meant to keep going, a 6.
We will not do demos.
So then a 6 would be, you know, communication repairs itself and you keep going. So if you have more dice, because your plan, you engineered the thing the day before was better, then it's assumed your life on the planet will last longer. And so you reward them that way, and you have a prize at the end and stuff. I think it's like $2,500 prize at the end or something.
You get that? And you got to remember,
There's a little pile.
I'm no smart. As I understand it, then this would be an interesting game, as I understand it, because while someone may start with 20, someone may start with 10.
Exactly.
10 may
Because,
last 20 because it's a probability.
to quote our mentor, he said the warranty on the rovers on Mars right now ran out after 90 days. And
Right.
so everything is bonus after that.
Yeah, because they're designed for a certain amount of time.
So they obviously over-designed, and they had the better design, and they're rewarded for it.
So the two ways, yeah, well, the two ways to look at that. One is you over-designed and you took more money and resources from the agency. You should punish.
True.
Or you got this bonus of time for it.
So I'm excited.
Yeah, that's a great game. But it's kind of flipped around the other way from this. It shows that no matter what, it can last longer because of luck.
Yeah, which is what happened.
Okay, thank you. Guys, how do we do here? How are we doing here?
We've got the herd to end all herd,
Bad
so
engineering.
we still haven't
Very.
gotten past.
Well, just tell me what happened.
First one was
Poorly
17.
designed. It doesn't fit.
All right. Then we went back to 19, and we got all the way up to 20 again. And we dropped down to 17. Then 14, another 14, 13, then 9, back to 12, 11, and 12. No, years, 11.
Yeah.
All right, now, I know that you guys do according to the rules, but sometimes I might say that this is kind of an outlier of cases. I mean, it may not. I mean, you're right, but you also would look at something that's an outlier because most of them will be more like this. But you know, this can certainly happen. It might be that the next day, next year, you suddenly go down to 2 and 1, and you're back on. So, but yeah, but what it does show is that you know this general shape, and if you kept going, eventually you would die out, and that's the general shape of the extinction.
You guys need to go to Las Vegas. Just got back recently and it didn't work.
So, and so the other thing you can do with this is you can change the probabilities. You can show, I talked the other day about, suppose you have a human hunter. The mammoths were existing just in a world of, you know, idyllic, you know, they eat and they reproduce and they can have some bad weather or something like that, they can starve, or they have other predators. But what if you introduce humans and the humans decide we want mammoths? Mammoth, you know, they're great clothing, it's great food. And so what you could do is you could change your 4, which was the mammoth lives, you know, another year and nothing happens. Change the 4 to killed by human hunter. And now you've got 3 ways the mammoth could die. So you increase the probability. Now, obviously, it's not the same probability. It's not 1/6 they're going to starve, 1/6 the human hunter. But the idea for the kids is I introduce a new way for them to die, a new probability. So now I've got 3 ways they can die and 1 way they can have births. And what you'll see, of course, is that I can't tell you to be secret in these, but normally what you'll see over a number of tables doing this is you'll see a steeper extinction. There are more ways to lose than there are to gain. And so you can show the impact of humans to the herd, which is kind of a geography.
It's better than our arrow thing.
So that's why I say this isn't just for STEM, this is for all classes.
It's better than our
Any questions on that? Comments? Okay. Let me now do
in terms of everything.
the theoretical version of this thing. So this is what happens, and I like this because you create your own data set. You know, in data sets, instead of being given something, you actually create it. It's pretty straightforward to create it, and there is no right answer, you know, because it's probabilities about. These are the right answers. There are a lot of right answers, probabilities. So let me go do one now that's theoretical, and I'm going to use a program. I have to get out of this, and.
You want to change?
Yeah.
Turn off your overhead projector.
May I have my overhead projector back, please?
We do have a big screen.
This one? Yeah, but you're not going to be able to see it very well. Oh, I bet you. Is that the projector, or I just hadn't refreshed it enough?
They'd have to measure center of gravity. And they want to do that on the rocket and all that stuff too. Things like that.
Okay, good, thank you. So what we're going to do here is, so that was an elementary school project, but I think it's nice for all grades. Now here, for your middle and high school kids, certainly high school kids, is a way to do this theoretically with a piece of software which is reasonably accessible to schools. You can get a site license for around $900, which means the entire school. PTA can support this. I know you can't have a $3,000 head football coach and a $900 set of software, but the PTA can maybe bring you the software from up face. By the way, I found when I was on the school board, local school board, that the best way to get money for reading teachers is to ask how many assistant coaches we have for our football teams. Just asking the question was enough to have the superintendent find money for reading teachers. It was amazing. It was like magic. So you go to this software I just opened. It's called STELLA, and it's called a stock and flow software. Did anybody watch? There was a Rachel Maddow show on MSNBC, I don't know, 6, 8, 10 months ago, a year ago, and she made fun of, which angered me because it was a really anti-intellectual thing. She made fun of this chart that had been created by the DoD on the Iraq War or Argentina. It was something. It was all these flow diagrams and arrows and stuff like that, and she just sat and made fun of it. Well, what it was a simulation. It was a model of the war, and it had things like the weather and logistics and enemy strength and all this. They tried to model the battle space for the war. That's what they do these days, the DoD. They used to have these sand tables where you push the battleship here and you push the troops there. Now they have these big simulations, which actually they show on big touchscreen sand tables that are like the size of these tables and move things around. So, and they can underlie, they put real Google Earth maps under it so they can see where things are too. So what you do in this is you go to the model page, it's called, and the reason I like this simulation is it's so simple. Compared to things like MATLAB and Matrix X and these other things you use, this has 6 icons, only 5 or 6 icons. And the icons are, unfortunately,
Is this STELLA?
shit. All right, so the icons are right up here. That's okay. The icon's right up here, and there's basically a rectangle, and I'll bring them down. So you have a rectangle, a flow pipe, a circle called a converter, and a connector and a decision box. That's it. That's all you have to learn to use this. So that's nice.
Down a little bit so we can. those icons.
I just tried to do that.
Shrink it from the bottom and then pull it down. See if you can do that.
I don't really want to shrink it. I know.
And you got the dock floating around there. There you go. Grab that.
I know.
Can you see on your screen the little green button that's on the top of the window? Oh no, you have a, yeah, you have a Mac.
They can use the ball, ping pong ball, whatever.
All right.
Is there a little green button way at the very top on the left hand side?
Yeah, I don't want to shrink it too much because I need the screen now.
Certain points, and this is the number of
I think it just puts itself at the top. So anyway, it's not that important. Because I'm going to use the things right now. You'll see what they are. So it's called stock and flow. This is called the stock. It's a rectangle. You grab it, you put it in the screen, and the stock is how much of something you have. In this case, the number of mammoths. So we're doing the mammoth here. So that's the number of mammoths. So I'm going to just write that as mammoths. Okay, and ignore the question mark for a minute. I'll fill in all the question marks. Now, for this mammoth herd, it's called stock and flow. I have flow into the herd and flow out of the herd. So flow into the herd are births. And so I'm going to put, it's like a pipe. Looks like a pipe with a valve on it. There. I'm going to call that births. And I don't expect you to learn how to do this watching this. I just expect you to see that you can do this, and then you could go out and get the software. And actually, for free, they will give you and actually this is save disabled. For free, they'll give you a save disabled version that you can practice on. You just can't save the stuff you do, but you can practice doing it. So they're very, very education friendly at this place. So those are births. And now the outflow, what goes out of the stock or the herd, are going to be deaths. It's also known as system dynamics software. So I have births that flow into the herd, deaths that come out, and now I have to somehow get the information in as to how many of those there are. So there's this, I use this converter, so now I've used 3 of these things, which will be birth rate or probability. Birth rate or probability of a birth in our case. And then deaths will be determined by the death rate or probability of death. And now I have to connect those, which means I use a connector. Connect these things into the birth. I have to get the birth rate connected to births. Oops.
STELLA.
Oh, I'm trying. They emailed me.
And I have to get death rates connected to deaths. And now we think about it, and there's something else I need to know, because they're not just a death rate or a birth rate of 1 mammoth per year or 6 mammoths per year or something like that. What else do I have to know to determine how many mammoths are born and how many die? What influences that other than this probability?
How many you start with?
Yeah, how many you have, right? Yeah, so how many you have. So it's not just 2 mammoths a year or 3 mammoths a year. So this death rate I have and birth rate is really a probability of birth and probability of death. I should have written it that way. So I need to know here, to get the number of births, I need to know how many mammoths I have. So I connect the number of mammoths into the birth. So now I have information about this birth rate or probability of birth with the number of mammoths. That's the information I need. And I do the same thing for deaths. In order to know how many mammoths actually die, I need to know how many are there. These connectors that I've taken from the mammoths to the dynamic, to the flows, are known as feedback loops. They're known as feedback loops in the world of control. Okay, it's connecting that information. That's what makes this different than an algebra problem. So now, I just need to fill these in. I start with initial value of mammoths is 20. the birth rate or probability of birth is, what do we say, 0.17, 16? 0.16, 0.17?
Yeah, 0.17.
Yeah, 0.17. So you could do 1/6, but we'll do 0.17. Oops. All right. The probability of death is what?
0.34.
Yeah, 0.33 or 0.34. And the nice thing about engineering is 0.33, 0.34, you won't see a difference. If you do, then you worry about it. Okay. And now, births, it says births equal. And the right-hand side of the equation, you have to use these inputs. So it's mammoths times birth rate, or the probability. So the number of mammoths times the probability. Right. And then on the death flow, outflow side, it's mammoths times death rate or death probability.
And you don't see birth rate because it's not in that feedback loop on the right side going to that valve.
I mean, over here?
Yeah.
Yeah, I don't care about.
No, I'm just saying when you had that window open, you had only two options, and neither one of them was birth rate, and that was probably because the software knows it's not.
Right.
Have a connector.
Yeah, that's right. You're exactly right. It shows you what's connected. You're exactly right. Yeah, it shows you what's connected and what you have to have. It's nice in that way, and that also helps you understand. And then the people who do this a lot when they do it with high school kids, make the kids do units and make sure that when you're multiplying things, the units come. And when you multiply all these pieces together, that the units should come out to mammoths, not furlongs per fortnight or something like that. That's when Juan talked about SI units. I told him that English units to me are furlongs per fortnight. I had an old engineer that explained that to me. Okay, so here we have it. This is the chart. This is the simulation that represents what we did. And now I just have to set up what's called run specs. And now let's run this from 0 to 25 years. So 0 to 25, and I can choose kind of the stuff I want. I'll call years. These integration methods, has anybody in here heard of Euler's method or Runcutter methods? Anybody?
Yeah.
Yes.
That's what we're
No,
doing.
not at all.
That's what we're doing.
Are you doing that where?
Our lesson plan.
Okay, great. Because normally, when you get to a group of teachers.
I know that because our mentor told us that.
Okay, so I didn't know about this until I came to NASA. I taught high school for 5 years, math, science, advanced, taught AP courses. And I knew Euler's method because I'd done that in college for some reason, but I didn't know Runcutter. So I learned this when I got out here and how to do these things. But so these are things that normally teachers don't get in their teacher training or even if they take math and science degrees. So we'll just use Euler's. It's fine for this. And now they have a really nice graph that comes up, and it goes up to 25 years, and almost done. And now I want to
That first thing they downloaded, there was like all the stuff you have to do to get there.
select mammoths to look at. And you could select to look at deaths, birth rate, any of the things you have on there, you can look at the time history of those things. But I'm just going to look at the time history of the mammoths because that's what we have up here. Okay. And now all I do is hit, hopefully, run. There it is. So what you see is, it starts with 20 mammoths, comes down to extinction in about 25 years here, and this has a nice feature that I can, like at 6 or 7, I can look here and it says I've got 6 at 6.5. I've got 6 mammoths at 6.5, and here these guys were right here. They're both about that. So this is a nice, and so if I took that drawing and I put it here, it would kind of look like this. It would kind of interpolate these two, not you guys, with your healthy herd over there. Yeah, it's healthy herd. But interpolate these guys nicely. So the thing I like about STELLA in this modeling simulation, the theory, is that it has a probabilistic model that gives you kind of the same, or gives you a theoretical result that mimics the experimental result. It fits the experimental result in some way. Now you can make it, they have capability within STELLA to have each point a probabilistic pseudo-random selection to do some things too. So you could mimic your dice throws. So you can put some noise, if you like, on top of this too. You can mimic your dice throws. But I just think it's a nice way to say, okay, I did this experiment, I got these things in the experiment, here's a theoretical model that approaches it, and I get a nice smooth result like that, but it's the same behavior in the long run. Yes, sir?
Software, do you know if it's like school-wide where you can load it on 30 laptops or you have to pay 30 times?
No, that's right. It's a site license. You can have 2,000 kids in a high school, $1,000. It's a site license. Yeah, it's a site. That's the nice thing about it. Yeah, I see, and I'm going to leave you books.
You can download a free trial too.
Right.
Is it STELLA?
Yeah, just STELLA software is what, or STELLA simulation is what I Googled. I just Googled it.
And the user support people there, and particularly the lady in charge of that, is very, very friendly. Tell her my name and she'll help you out. These are the books. These are 2 books by a math teacher in Portland, Oregon. And she's been doing this for like 20 years, started with an NSF grant. There are lots of examples in here teaching math and teaching science. So I will leave these and the change book here today, and I'll pick them up Monday when I come back. Any questions on, so by the way, so why is this neat? You can play what if games. So what if I decide that the human hunter comes in? So now the death probability is what? 0.5, yeah, it's half. 0.5 now, because now I introduce a human hunter. I don't have to do another experiment. So introduce a human hunter. And now watch closely, you watch the graph shift. So now I'll just run, and you can see the graph shift down. Here, shifted from about a 6 here down to about a 3 here. So you can see the introduction of the higher probability, and kids can play a game with, okay, what if I had this, what if I had that, different probabilities. They can go to the internet and find out what real probabilities would be, what the real impacts are. So they can really do an impact on the world. They can do, there's a thing called World 3 that exists out there, which is a model of the entire world and resources and how those resources will play out over the years. Those games. So it's just a kind of a neat thing to get kids do this. Any other questions? Comments?
You mentioned man hunting. I teach English, so here I am with this math stuff. But the dangerous game, the man hunt, you could put literature into this probability factor too.
Yeah, you can put any number of Rachel Carson's, the silent seas, silent spring, yeah, and sea around us, silent spring. All those things, those early reports of the 60s and 70s and impact of humans on environment, yeah, that's perfect for modeling this way. Drugs going into your system, alcohol in your system, they go into your body, they stay there a certain amount of time, they go in your stomach, they're released to the rest of your body. Whether you take shots, pulse, introduction of drugs, or if you have an IV, a continuous introduction, or take pills that have to go to your stomach and then you can model all those things and figure out what kind of doses are lethal, what kind of doses are effective, and and play those games with this. And she has, Diana Fisher, who did these books, has examples of those. Any other questions on STELLA? We're almost done. All right, so the summary is modeling simulation is used widely in the industry. I gave you lots of examples. It gives the student a feel for the dynamic behavior over time. So that was the idea of the STELLA example. The idea of this is that how things behave over time. They're not just single examples. And it can use these feedback loops and tie stock to behavior. So it recomputes and recomputes, which is basically, as Juan said the first day, ordinary differential equations or calculus. So it allows our kids taking algebra to solve problems that would have taken knowledge of calculus 10 years ago. Okay, yeah, I thought I had this. So your connection at IC Systems, which are the people who do the STELLA software, would just be to email support at IC Systems, and Joanne Egner is the person, or just if you do support, say that I said that Joanne would help you out. And you're at a NASA program, and she'll be glad to help you. Or you can go to the Creative Learning Exchange, which has a relationship with IC Systems.
I'm looking at it here, and it's the free trial software.
Yeah.
Disables after 30 days.
Right.
You could get a regular sale disabled for $50.
The regular.
It still disables safe, but there's no timeline on it.
They'll work with you on that. That may be what they say there, but they'll work with you on that. Yeah. I think they just don't want people coming in and grabbing it. And if you have trouble, just give me a call and I'll help you out. All right, so just finish up here with a few more slides. We've got some other ongoing activities here regarding K-12 education. One of them has to do with modeling simulation. I think you're going to be asked, if you haven't been asked already, as you finish up stuff in this program and you get lessons that look like they're useful in modeling the simulation to classes, to provide a chapter of a flex book or somewhere sorry, that's okay. So my grandchildren books are to be used. This is a hard copy of a flex book, and I'm going to talk about it in a minute, but we want to put out a modeling simulation book which gives useful modeling and simulation information for all teachers to have access to. It would be freely available on the web. It's a Creative Commons license like Wikipedia, share alike. And so we're right now in the process, Bezod is kind of leading the project to get authors to contribute to this book. And I'll tell you about that in a little more in a minute. Sharon Welch, who had done some leadership in this program until about last month, is in Washington at Achieve Incorporated. Do we know what Achieve Incorporated is? Anybody? They're the ones who developed the American Diploma Project, the first Common Core standards, and they did it over the last 15 years in math and English language arts. So they're a nonprofit the National Governors Association had created. They've gotten the contract to take the National Research Council outline that came out the other day, guidelines, and actually create the next generation science standards. Sharon is up there. Remember the first chart I had, the three-legged stool of subject matter experts, K-12 people, and okay, she's up there as a subject matter expert on staff for a year on loan from NASA to help them as they put these together to be an engineer scientist there. They've also hired a scientist on staff so that they get the content right. So we did in Virginia in 2007, and they kind of liked that. So they've got some people up there. So Sharon's up there doing that for the next year. The Flexbook, this is a picture of, in 2007, when our panels of engineers and scientists and physicists and chemists met, we had people from universities, government labs, and industry all there, but we also had a couple of K-12 teachers on each panel just to kind of keep us, with ground truth. So we said, well, they've got computers in the schools, they can do this. And then the K-12 teacher said, yeah, but you can't use the computers for this stuff. They're busy having them test and things like that. And, you know, we have 36 weeks in a year. Well, not really. We have really 28 or 30 because we do these things. And so the teachers were there, and they really helped us understand what the limits were in the real world of schools. And the teachers also told us something interesting. The physics teachers said, hey, look, we agree with everything that's going on here, that kids need to learn about quarks, and the kids need to learn about modeling and simulation, and that organic chemistry has to be in the chemistry course in a world that is, you know, virtually all molecular biology, because they'd taken organic chemistry out of the chemistry in Virginia in 2003, the people who reviewed the standards then. And so they said, but however, plasmas should be in there, not just solids, liquids, and gases. And so, but these teachers said, we'll be fine. You know, the three of us or so, 2 or 3 of us in this room would be fine. We'll go to the web, we can Google, we can put curriculum together that'll do this. But they estimated that 40 to 50% of their colleagues would need a resource, a book or something. They would not be able to create their own curriculum. That was the teacher's estimate. And they said it would be really good if we had something for them. We said, no problem. You know, we'll just have the Department of Education, they're interested in this stuff. The Virginia Department of Education support a wiki. You guys and gals, the top teachers, can write the curriculum, put it on the wiki, and all the other teachers can then use it. Well, the Department of Education said, oh, no, we can't do it. God, things can go wrong with a wiki. Who will monitor it? Someone could put obscenities on it. You know, they had all the reasons you couldn't do this thing. So at that time, the Secretary of Technology for Virginia, who is now the President's Chief Technology Officer, a guy named Anish Chopra, who I was sitting here across the hall from the Secretary of Education, who I worked for, and Anish was 25 feet down the hall. Anish says, wiki, that's technology. I can help you with that. So he put us in contact with this group called K-12 Foundation, a nonprofit in California, and they make these web-based books called Flexbooks. A flexible text, Flexbook is a flexible textbook. It's flexible in the sense that you download the text. It's Creative Commons license, so anybody has access to it, just like the Wikipedia. You can download a chapter. The Flexbook platform allows you to edit the chapter. So as a teacher, you download a chapter, let's say on particle physics, and you say, oh, this is really good. This is good, but gosh, I wanted to put in something that I knew from so-and-so. Well, all you do is open your chapter, and it's your chapter, and you edit it. You can take things out, put things in, you can customize it to make it your chapter. So you have a basic book of information that you can then customize to your needs for yourself and your kids, update it whenever you want. It's always on the web, and you know, in the web edition can get updated over time too. So that's called a Flexbook, a flexible textbook. So here are a couple of pages. Here's something on the standard model in particle physics, one of the pages we put together. Here's a thing on the nano chapter, nanotechnology chapter, nanoscience, telling people, well, what is this nanotechnology? What does it mean? How do nano things compare to other things you know in the real world? So this gives teachers a reasonably vetted set of examples. So that's what we want to do for modeling simulation. That's kind of my final note. And hopefully you guys will become authors in this. If you can do a national teacher license, teacher certification type thing, this could be part of your portfolio. I would assume a chapter in a book would be a decent thing to have as part of your overall portfolio. And for the people who do this, when we get this thing actually published and done, there will be a celebration reception at the old executive office building, which was on the White House grounds, that Anish is going to lead. He's excited about this. He said he will absolutely lead and host the celebration for the authors come fall or winter when this thing gets done. So you get to meet the President's Chief Technology Officer at the old executive office building. So anyway, we're hoping this will work out. We're hoping. So a final note, a good approach to this, my final note for this is,
Just Google that.
if you're doing modeling simulation, these things in your school, the best thing is to have in each school, certainly in each school division, is to have a subject matter expert. And so that's someone who gets familiar, learns the literature. You're the go-to guy or gal for your school or for your school division. You learn the literature, things like the books I've talked about here, Quaiden and Tarkovsky's Shape of Change book, Diana Fisher's books, and others. IC and Creative Learning Exchange are two groups that have conferences in system dynamics and modeling simulation every year. Go to one or two of their conferences a year. They're, you know, West Coast, East Coast, all around. You know, keep up, network with some people. You become familiar with various options and software and requirements, and get your IT people or IS people comfortable with having some of this stuff on your computers. And so I've just got a few of them here. There's lots of education specials. You be the go-to person for questions on this stuff. Develop a community of learners. And finally, don't forget, in the midst of all this, the CAD/CAM, Computer-Aided Design and Manufacturing. Because your shop classes, your CTE classes are heavily involved in that, and it'd be nice to make this relationship between the two worlds. Because that's modeling and simulation too. My favorite story from a Project Lead the Way class was when they first did the three-dimensional model on the computer, the CAD, and then they sent it over to the printer, you know, to be built up, and the kid goes over and he takes the piece out and goes, "That's not what I designed." It looked like it, you know, in 3D, but it didn't quite come out the same. So, you know, that's kind of a real world versus a model situation. So that's it. Any questions?
Is this PowerPoint available to us?
Yeah, it should be. Where's?
Oh, she hasn't been here for a while.
She has it, she told me to bring a jump drive. So. Is that right? No.
It's on the jump drive, or
Or you can bring your jump drive in and then
I thought they were giving you copies of all this, but yeah, it will be.
I don't know.
Couldn't
Your
find
earlier
it.
one this week is on the,
Okay, I'll make it available. I mean, it's going to be available. I can put it on somebody's stick here before I leave. But it's made to run on the Mac, so there may be some graphics that don't show up, pictures like on a PC. So, because I didn't copy it right. I can do. Let me take just one more second here. Obesity. This is another model using. I have this as a backup slide, but. And I did this on Monday. So this is, now you should recognize this. This is what I had Monday. And this is put together just like I did the Mammoth game using STELLA. So this has to do with obesity. The stock is body weight. Inflow is pounds or calories eaten per day. It's how you gain weight. You lose weight because you exercise. Okay, so this is pounds burned per day exercise, but also resting maintenance just to keep your body alive. But we also know, again, a feedback loop, keeping your body alive depends on how much body there is to keep alive. You know, how many mitochondria have to be fed in your cells. So there's a feedback from body weight into resting maintenance. So all these things tie together. And actually, there's also one to exercise, which has a different component. So this is another thing you could do with your classes using STELLA. And I show, if you don't have the feedback, this is one, if you don't have the body weight feedback, over a year, ingesting 3,000 calories a day, and assuming you just burn 2,000 and do it when you exercise, you end up gaining, over 360 days, to almost 300 pounds. Right? Because you have 1,000 calories a day net, and you have almost 300 pounds. If you just put the feedback loop in without any exercise, I'm preparing you for lunch. 235. That's just feedback. That's the importance of that feedback loop as you get heavier, and it's a it's a control. It shows you can't get heavy forever. It takes you more energy to eat than you can support. And finally, if you put exercise in, you can actually maintain. Do enough exercise, you can maintain 170, and that allows kids, like I did with changing the probability of death. Yeah, you've got to run about 6 miles a day. And you can put age, I mean, the kids can put anything they want. So that's my point, is that this is another really nice use of the STELLA software. And that's it. Okay. Any other questions or comments before lunch?